All right, here's lesson 3 on patterns and linear functions. We want to see understand some vocabulary first here. We have things called dependent variables, and we have things called independent variables. And a dependent variable is what's going to change in response to the independent variable. I know this sounds a little confusing, but it'll make a lot more sense as we go through this. Any value that's assigned to an independent variable is called an input. These are our x values typically. Any value assigned to a dependent variable is called an output, and that's our y value typically on a graph. So the independent, the ones we can choose, are our x values, and then we put that into our function machine and it spits out a value, and that's our y value. That's our dependent, and we cannot choose that. That's the machine creates that for us. So remember the sneeches from the other day. Okay, I have the words input, x values, independent. Okay, these are what are going into our function machine. Now in the case of this function machine, its rule was add a star. So kind of a +1 machine, if you would. As the sneeches go into the function machine, whatever goes in, a plain-bellied sneech, comes out with 1 star on it. So this is a function machine. It does the exact same thing to every single sneech. It gives it 1 star. It's the +1 machine. Over here you see what's coming out of the machine. These are the y values, the outputs, the dependent variables. Now we can't choose. We can't say, oh no, it's going to come out with 3 stars or it's going to come out with 7 stars on its belly. We cannot choose this. We could, however, choose to put a sneech in with 4 stars already on its belly, and it would have to come out with 5 because the machine is adding 1 star. So as long as whatever goes in comes out, then this is a function. Whatever goes in, remember, it has to, for every single piece of the domain, has to match up with exactly one thing in the range. Let's look at representing a linear function. Now the word line is in the word linear, and that's really important here. Anything that's linear is going to give a graphic, the graphic representation of that is going to be a line. So starting off with this table, and we've already seen how tables and graphs and mapping diagrams and all these things are all one and the same. They're all just different ways of representing data. So this table here shows the relationship between the number of photos, x, that you take and the amount of memory, y, in megabytes that's left on your camera, on the camera's memory card. Is this relationship a linear function? Describe the relationship using words and equations and a graph. So let's take a look here. How would we know if this is a linear function? Well, first thing we'd have to do is determine if it's even a function. So let's just kind of take a look here and see. If I put 0 in, I get 512. If I put 1 in, I get 509. If I put 2 in, I get 506. If I get 3 in, I get 503. So everything that's in the domain, my x values, is matching up to exactly one thing in the range, my y values. Therefore, this is definitely a function. So we're good so far with this thing being a function. Now we have to determine whether or not this is linear. And the way we know if it's linear is if we see a pattern that's the same pattern going on in the x values, and then we see a pattern going on in the y values. And when I say a pattern, there has to be something very important here in this pattern. There has to be the same number. It's going to be called the common difference. Okay, so let's take a look. Between the numbers 0 and 1, how do I go from the number 0 to 1? By adding 1. And how do I go from the number 1 to 2? Again, I add 1. And going from 2 to 3, once again, I'm adding 1. So there's a pattern going on here, in my table every time the next number is increasing by 1. Okay, so that's good. So on my X column, my domain, everything's increasing by 1. Now let's take a look at the range. Going from 512 to 509, I'm subtracting 3. And going from 509 to 506, I'm again subtracting 3. And going from 506 to 503, I'm once again subtracting 3. So you can see that the dependent variables here are decreasing by 3 each time x increases by 1. Since there is a continuous pattern here, this minus 3 every single time, and it's a plus 1 here every single time, since that pattern exists and the number is the same for the domain, and then the number is the same, even though it's a different number for the domain and the range, the number within the domain, how it's increasing, the number within the range, how it's increasing or decreasing, as long as those numbers are the same within their own group, then this is going to become a linear function. So let's take a look at words. How can I write what's going on here in words? So the amount of memory that's left on this chip is going to be 512 minus the quantity that's 3 times the number of photos taken. Let's see why. Let's see that. The amount of memory left on this memory card chip is 512 minus the quantity 3 times the numbers of photos taken. What does that mean? Well, let's try to put that into some sort of math equation. Let's see. Get a spot here to Alright, so what are we saying? The amount of memory left on the chip is, the word is means equals, right? So 512, or the amount of memory is going to be y, so let's erase that. Right? The amount of memory left on the chip. This is the y column, the range column. So y is, and then I have 512 minus the quantity. Whenever you see the quantity, it means it's going to be multiply, and it's whatever comes next. So 3, and it already says times the number of photos taken. So let's see. The number of photos taken is x. So we have y equals 512 minus the quantity 3 times the number of photos taken. So 3 times the number of photos taken is x, 3x. So here is an equation. And if you remember a little something from 8th grade from last year, you'll remember there's something called y equals mx plus b, and that's the equation of a line. And right now, I have that. I have the equation of a line going on here. I have y equals some sort of, here's my mx piece, and here's my b piece, just in the different order. So this is definitely going to be a linear function. Let's try to graph this now. Over here on my graph, going down this side would be my y-axis. Going this way would be my x-axis. Down here, let's call this 1, 2, 3, 4, 5, and so on. And counting up, I'm going to skip a whole bunch of numbers and go all the way up to, let's start at 500. So 500, 502, maybe I should count by 2's here. Let's see, 504, 506, 58. No, I can do this. 504, 506, 508, 510, and 512. Alright, so let's see how this graphs. Well, the number 0, which would be here, goes with 512. So I'll use red to try to show it up. So all the way up to 512 at 0 would be a point up here. At 1, the number that matches with that is 509. So 509 is between 508 and 510. So that's going to be right here. At 2, I have to go up to 506. So that's right here. And at 3, I go up to 503, which would be right here. Now, the neat thing about a graph is it can help us predict values for the future here. So let me see. Since this is a straight line, this is a linear function. That means these points should all be in a straight line. So let me try to use a straight line tool here and determine if that's true. So by starting, let me use a color. I'll use orange. Let's see if I can connect. Look at that, straight line. And if I kept it going, I can make some predictions. I can predict that if I took 4 pictures, I should have, at 4 pictures, I should have exactly 500 megabytes left right there. And does that make sense? If I added a section to this table here that said 4, well, I'd have to subtract 3 more, and I'd be at 500. So my table makes sense over here. My graph makes sense. Linear functions, the dots will all create a straight line. That's how you know it's linear. And that's really it for this. So let's try and make sure we understand what's going on here. Using this diagram below, we want to complete the table. So using this diagram with these squares in it down here, we want to make sure, we want to complete this table showing the relationship between the number of squares and the perimeter of the figure they form. For example, the perimeter of this square is 1 plus 1 plus 1 plus 1, which is 4. So when I have 1 square, I get a perimeter of 4. So with 2 squares, this would be 1, 1, 1, 1, 1, 1. So that's 6. So with 2 squares, I have a perimeter of 6. So you need to try and figure out what the perimeter for 3 squares would be, for 4 squares, for 10 squares. Find out what the number of squares would be to make 62, perimeter of 62, and then try to generalize this by saying if you had n squares, the perimeter would be something times n or something plus n in some way like that. So the perimeter for that bottom right corner is going to involve the variable n somewhere in it. All right, good luck, have fun, and I will see you next class.